Chapter 16 Online Mechanisms Abstract Online mechanisms extend the methods of mechanism design to dynamic environments with multiple agents and private information. Decisions must be made as information about types is revealed online and without the knowledge of the future. In the sense of online algorithms, we first consider single-valued preference domains and characterize the space of decision policies that can be truthfully implemented in a dominant strategy equilibrium. Working in a model-free environment, we present truthful auctions for domains with expiring items and limited supply items. Turning to a more general preference domain and assuming the existence of a probabilistic model for agent types, we define a dynamic Vickrey-Caloric growth mechanism that is efficient and Bayes-Nash incentive compatible. We close with some thoughts about future research directions in this area. Introductions: the decision problems in many multi-agent problem domains is inherently dynamic rather than static. Consider, for instance, the following environments: selling seats on an airplane to buyers arriving over time, allocating computational resources like bandwidth, CPU, etc. to jobs arriving over time, selling adverts on a search engine to a possibly changing groups of buyers and with the uncertainty about the future supply of search terms, allocating tasks to a dynamically changing team of agents. In each of these settings, at least one of the following is true. Either agents are dynamically arriving or departing, or there is uncertainty about the set of feasible decisions in the future. These dynamics present a new challenge when seeking to sustain good system-wide decisions in multi-agent systems with self-interest agents. This chapter introduced the problem of online mechanism design, online MD, which generalizes the theory of computational mechanism design to apply to dynamic problems. Decisions must be made by dynamically and without knowledge of future agent types or future decision possibilities in the sense of online algorithms. Example: dynamic auction with expiring items. Consider dynamic auction model with a discrete time period t, which is equal to the set 1, 2, 3, and so on, and a single indivisible item to allocate in each time period. The type of an agent I, which is in, chosen among the set 1, 2, 3 until capital N, is denoted as theta I equals to the tuple AI, DI, and WI, where is defined in the domain of t times all those r rational number which is greater than 0, a positive rational number. An agent I has arrival time AI, departure time DI, value WI for an allocation of a single unit of the item in some period t, which is defined in the closed interval between AI and DI, and wants at most 1 unit. This type information is all private to an agent. We refer to this as the canonical expiring items environment. The arrival time has a special meaning. It is the first period in which information about the type of this agent can be made available to the auction. We say can be made available because a self-interested agent may choose to delay its report. Assume quasi-linear utility with the utility Wi minus p when the item is allocated in some t, which is in a closed interval between AI and DI, the arrival time and departure time, and a payment p is collected from the agent. Consider the following naive generalization of the Vickrey auction to this dynamic environment. Auction 1. A bid from an agent is a claim about its type. Theta I hat equals to the tuple AI hat, DI hat, and W omega I hat, necessarily made in a period t which is equals to AI hat. Then in each period t, allocate the item to the highest unassigned bid, breaking ties at random. Collect a payment equal to the second highest unallocated bid in this round. So example 16.1. Jane sells ice cream and can make 1 cone each hour. The ice cream melts if it is not sold. There are 3 buyers with types 1 to 100, 1 to 80, and 2 to 60, indicating arrival departure value. Buyers 1 and 2 are willing to buy an ice cream in either period 1 or 2, while buyer 3 will only buy an ice cream in period 2. In this example, if every buyer is truthful, then buyer 1 wins in period 1 for 80, stops bidding, and buyer 2 wins in period 2 for 60. But buyer 1 can do better. For example, buyer 1 can report type 1 to 61, so that buyer 2 wins in period 1 for 61, stops bidding, and then buyer 1 wins for 60 in period 2. Buyer 1 can also report type 2 to 80 and delay its bid until period 2, so that buyer 2 wins for 0 in period 1, stops bidding, and then buyer 1 wins for 60 in period 2. In a static situation, the victory auction is dominant strategy truthful because an agent does not affect the price it faces. But in a sequential setting, an agent can choose the auction in which it participates and thus choose the other agents against which it competes and in turn the price faced. In fact, if every agent was impatient with DI equals to AI, the departure time equals to the arrival time, then prices in future periods are irrelevant, and the dominant strategy is to bid truthfully immediately upon arrival. Note also that buyer 1's manipulation relied on a suitable bid from buyer 3 in period 2 and will not always be useful. Nevertheless, this serves to demonstrate the failure of a dominant strategy truthfulness. The challenge of online MD. The dynamics of agent arrivals and departures, coupled perhaps with uncertainty about the set of feasible decisions in the future and in general about the state of the environment, makes the problem of online MD fundamentally different from that of standard offline MD. Important new considerations in online MD are as follows. 1. Decisions must be made without information about agent types not yet arrived, coupled perhaps with uncertainty about which decisions will be feasible in future periods. 2. Agents can misrepresent their arrival and departure time in addition to their valuation for sequences of decisions. Because of this, agent strategies also have a temporal aspect. 3. Only limited misreports of type may be available. For instance, it may be impossible for an agent to report an earlier arrival than its true arrival. More generally, online MD can also model settings in which an agent's type is revealed to itself over time, and with its ability to learn dependent on decisions made by the online mechanism. For example, a bidder needs to receive a resource to understand its value for the resource. There are two main frameworks in which to study the performance of online mechanisms. The first is model-free and adopts a worst-case analysis and is useful when a designer does not have good probabilistic information about future agent types or about feasible decisions in future periods. The second is model-based and adopts an average case analysis. As a motivating example, consider a search engine selling search terms to advertisers. This is a data-rich environment, and it is reasonable to believe that the seller can build an accurate model to predict the distribution on types of buyers, including the process governing arrival and departures. So in section 16.2, we present a general model for online MD and introduce the concept of limited misreports. Given this, we define a direct revelation online mechanisms together with appropriate notions of incentive compatibility. Section 16.3 provides a characterization of truthful online mechanisms in the restricted domain of single-valued preferences and gives detailed examples of truthful dynamic auctions. These auctions are analyzed within the framework of worst-case competitive analysis. Section 16.4 considers general preference domains and defines a dynamic Vickrey-Clark groups mechanism that is efficient and applicable when a model is available and common knowledge to agents. Section 16.5 closes with open problems and future directions.